Hi everybody, we are talking about the chi-square test today, and there are multiple chi-square tests today. We're looking at goodness of fit and independence and homogeneity. But first let's talk about what chi-square actually is. So chi-square is very similar to a normal distribution, but the difference is that it has degrees of freedom. And so chi-square is always one-tailed. So it's going to be a test that still is unimodal, but it tails off towards the end. The higher the degrees of freedom, the more data points it has. The more data points it has, the closer and closer and closer that curve gets to an actual normal distribution. Okay? So when you look at the actual picture here on our image of our notes, the closer you get to normal, the more degrees of freedom you have because you have more data points. And we know that when you take a sample, the more sample points you have, the better and closer your actual data is going to be to the population. And so that's the way it works with chi-square as well. The closer you get to normal distribution is going to come when you have more data points and thus a higher degrees of freedom. Why it's called chi-square, I have no idea. But that's the name it's been given by its inventor, and so that's what we're gonna go with. The goodness of fit test is a test of whether the distribution of data, categorical variable, matches the distribution predicted by the model. We're seeing how well the sample we chose fits the actual population that we're looking at. So this is when you know something about your population. Say for instance, you know the normal percent of people that have heart disease, and you're looking at whether or not your sample has that as well. Whether or not your sample, your data, matches the population data. You have to already know something about your population, like the percent of people that have heart disease, or the percent of people that, what we're gonna look at here, have a certain blood type, right? And so that's what goodness of fit does, is it tests your actual sample data. In order to run the goodness of fit test, you have to have these assumptions and conditions that actually have them be met. And the first one is that it has to be counts. So data must be counts for the categories, not percentages. So we're looking at frequencies. We're going back to frequency again and all those frequency distributions that we talked about. And we're looking at frequencies instead of percent. So if you have percents, you're going to have to transfer those over into counts. The independence assumption says that each cell is independent of the other. One value in a cell is not going to impact another value. Randomization is coming from some population. Your sample is random. It wasn't specifically chosen to try to meet that percent. It was totally random. The sample size assumption, this is an important one. Okay, this says your expected cell frequency condition. So we have already found expected values before, and now we're going to have to find them again for our goodness of fit test. So what happens is you should, in order to run the goodness of fit test, you should expect to see at least 5 in each cell. So once you find your expected values, if they're not all at least 5, you have a couple options. Okay, option number 1 is not run the test. Option number 2 is to lump some of the categories together so that then that expected cell is at least 5 or maybe more. So for instance, when could you lump a category together? Well, that would be where you have several small, let's say that we're talking about favorite color. Okay, and you have like brown, or you have chartreuse or something like that, where there's only 2 or 3 people that really enjoy that as their favorite color. You can put those together and then make your category of other, right? And then that other category would have your expected values that are 5 or greater. Okay, so to run the test for the goodness of fit, you're looking at your chi-squared, which would be your sum of the squared deviations divided by expected counts. So we've already talked about standard deviations, and the sum of standard deviations, or the sum of your deviations gives you your standard deviation. So when we were doing that, we were saying how much a data value deviates from the mean. Now what we're saying is how much does our data value deviate from the expected value. And so when we look at that and we do that for everyone, then we're going to go ahead and average those out and end up with our chi-square statistic. So it's very, very similar to what we did with our normal distributions. So the formula says chi-square equals the sum of all the cells when you take your observed minus your expected, square it, and divide by your expected. So just like we squared our standard deviations before or our deviations before so that we could get to positive values, we're going to do the same thing here so that we stick with positive values. So here's our chi-square models. They are indexed by degrees of freedom, and to find your degrees of freedom or know your degrees of freedom, you're going to take the total number of cells that you have minus 1. So when you write out your data, you're going to have your category down the left side or across the top, and then you're going to have all of your cells in there. So if you have multiple categories for your categorical data, you're going to have multiple cells. So you have to count every cell in there, subtract by 1, and that's how many degrees of freedom you're going to have. So as I mentioned earlier, the more data you have, the higher your degrees of freedom and the closer you get to a normal distribution. But that's not where we're at right now. We're at chi-square, which is curvy. So again, you'll have to look at how much data you have. You can only use this when you are testing hypotheses. You do not use chi-square to make confidence intervals. It is only for testing hypotheses. So even if you are rejecting your null hypothesis, you're not going to go back and find a 95% confidence interval or anything like that, because you're strictly looking at expected versus not. Does it meet the population or not? Chi-square tests are always one-sided, as you can see by the picture, but the interpretation could take multiple forms, including a not equal to. When we dealt with normal distributions, not equal to would be a two-tail test. Chi-square is always a one-tail test. Most hypotheses are stated in words rather than symbols because we're talking about categorical data. So it's quite a bit more difficult to use symbols for categorical data. And then finally, this is where we come up with our actual test. If your observed counts don't match the expected, which they're most likely not going to, but that's why we find chi-square. How far off from the expected are they? So if your observed counts don't match the expected, the chi-square statistic will be large. Large chi-square values means lots of variance from the hypothesized model. Thus, if they're not very close, this will give you small p-values. Right? If the chi-square values are large enough, the p-values will be small and we will reject the null hypothesis. Right? Because remember, your null hypothesis is saying nothing's changed. The average of the sample is equal to the average of the population. Nothing's changed. So if we had a large p-value, that's when we would fail to reject. We would maintain that null hypothesis. But if we have a lot of deviation, so we have a very large chi-square statistic, and very large is always dependent on what your actual data values are. But if you have a large chi-square statistic, you're gonna have a really small p-value because your null says they're the same, so your alternative says they're different. And with a large chi-square, we have a small p-value and we will reject the null in favor of our alternative. All right, so here's how you actually find your chi-square. Step number 1, find the expected values for each cell by taking your row total times your column total divided by the grand total. Every single cell you have to go through and find those expected values. This is not something that is super easy and quick with technology unless you use a graphing calculator. Step number 2, find the components, compute the residuals. Remember, residuals is observed minus expected. Then you're going to square those residuals so that we're dealing with positive values. Step 3, divide each by the expected value and then sum them all to get your chi-square statistic. And step 4, find your p-value or your critical value. We can do that as well using the chart and test your hypothesis and see where you're at, what your result is. Or you're going to reject or you're going to fail to reject. And then I give you some instructions or directions on how to do this on Excel. And so we're just going to skip past that over to our next set of notes. Okay, so let's take a look at our first example for our goodness of fit. The example says the proportions of blood types O, A, B, and AB in the general population of a particular country are known to be in the ratio 49, 38, 9, and 4. Now that goes directly against one of our expectations already, where it says we need to have counts and not percents. Since that's talking about proportions, that's out of 100. So when we think about that in terms of percents versus numbers, we're going to have to kind of go back and forth with that to get them into counts. Then it goes on to say a research team investigating a small isolated community in the country obtained the following frequencies of blood type. And it says at alpha equals 0.05, is there enough evidence to conclude that the distributions are the same? So they gave us our sample data there, it's listed. And the very first thing that we need to do is create our chart. So that chart that I give you on these notes, that goes through the steps of how to find your chi-square. So it's just kind of a nice visual way for you to understand the steps. This won't be given for you ever again. It's just a way for you to start out. So we're going to begin with our observed, and we have our observed at the very top. It's very easy from our chart. So our first observed value is 87. Then we have 59. 20, and 4. Okay, so the next thing we need to find are our expected values. Since we were given a proportion in our problem, that's going to be a percent. So we can find the percent of our total 170 to find what we expect to have. So the very first one would be 0.49 because it is a proportion. So 0.49 times that 170 to give us 83.3. Then our next one would be 0.38 times 170, which will give us 64.6. You continue through your ratios. Okay, now that we have our observed and our expected, we can move on to the next step, which is finding our residuals, observed minus expected. So you'll take 87 minus 83.3 and 59 minus 64.6 to end up with those values. We'll get 3.7, negative 5.6, 4.7, the next step is to square them so that they're all positive. And finally, we're going to take that squared value divided by our expected value. Okay, so that is going to be ending up finding our average variance, kind of. Okay, but we're talking about a totally different distribution, right, which will give us these values. Okay, now that we have all those values, we add them all up to end up with our final chi-square statistic. So our chi-square, that's how you draw a chi-square, with a squiggle and then a straight line, is equal to the sum of all of these values, which is 3.2465. So that is our chi-square statistic. Now, is that a large statistic or is that a small statistic? Since we were dealing with such small numbers, we're not really sure until you actually look at your critical value. You find your critical value by looking at your table. In order to find that, you have to know your degrees of freedom. So remember, degrees of freedom is your total number of cells minus 1. If we look at our chart, we have 1, 2, 3, 4 cells, okay, or 4 data points if you want to think of it that way. So we have 4 data points minus 1 will give us a degrees of freedom equal to 3. Okay, so we have 3 degrees of freedom. So then we find our critical value. Our critical value comes from the chart. So if we go ahead and look at our chart, we're at, let's see, alpha of 0.05 and 3 degrees of freedom. All right, looking at your chart, your degrees of freedom go down the left side, and your probability, which would be your alpha, goes across the top. So we're looking at a tail probability of 0.05. That's what we're seeing as unusual. with a degrees of freedom of 3. So